In this presentation, I'm going to discuss about one of the most important paper on the deep learning history, which is in 2015, the batch normalization. Let's get started with the presentation. So what is actually today's content will be from four parts. First part, we will talk about the problem, which is the commonly known internal covariance shift. And the second is how does it come out with the batch normalizations. And batch normalization has a difference between training and inference. And the third part, we will talk about how to apply batch normalizations on the CNN. And for we will talk about the result, which provide a stronger and faster performance for training a neural network and stronger performance when you do the inference. So we talk about the first part is the internal covariance shift. So what is internal covariance shift? Later we will have a more intuition for that. But first, on the text definition is while training the neural network, each layer's input distribution change, and this slows down the training by the lower learning rates. Later, we will talk about that. And the solution for that is called normalization. So by using normalization, you can make sure that the distributions of the different features are close to each other, so you can apply with the higher learning rate for that. And I think that is the very intuitive concept because we all know from feature scaling techniques that showing in these pictures, right? So in the left side, you see there's a different scale of the features that some scales from 1 to 3 and some scales from 100 to 100. So of course that the result of the weights will be depending on the input scales. So if you can plot them into these loss functions, we just using two inputs and two weights because then we can plot showing on the 2D. And if you see these 2D pictures, there is a distorted, it's not a circle. So when you're trying to apply learning rate, you need to make sure that your learning in your initializations is right on a good place. So if you are showing here, if your initialization points are here, then you're probably gonna go into a zigzag path, going to the optimum solutions to a lower loss. So by applying the feature scaling, you make sure that you normalize this plot into a more circle-like shape. So no matter where you apply your first, no matter where you initialize your weights, you are good because all the shapes are relatively similar. And the second thing is you can apply a bigger um, learning rates. So because all the path will be go directly to the loss functions, and that is feature scaling, which we apply in all machine learning techniques and in all computer vision as well. You will normalize the input image size even on RGB image. So that is we already apply feature scaling on our input, but now we're gonna extend them into neural network architecture. So if we are doing the feature scaling on the input, why don't we do the feature scaling as well on the hidden layers? So before we talk about the feature scaling, that's only on the first steps on the input side or on all the data sets we do on the machine learning. However, inside the deep learning, we know we have a lot of hidden layers. And once the network architecture or structure goes deeper, then of course, then it will be benefit if we also applying the feature scaling here. And that is exactly the idea of batch normalization. Um, we want to apply normalization to all the hidden layers, and that solves the problem of um, internal covariant shift. Let me try to explain what is internal covariance shift. So if we see a neural network here, and let's say the input of X here. The neural network here has the input from the previous layers. And if the previous layers has the different distributions every single time. Let's say that at the time t you have distribution like that, the four inputs distribution like that, and then of course you will adjust your weights based on this distribution. And then the second times, the t plus 1, the distribution totally change and your weights is totally changed here again. So if you have such a dramatic change on your distribution in each input layers, then of course your weights will be changed all the time. And that is the problem, that um, it slows down the training process because all the time the distribution is changing and your weights need to readapt to the whole situations while training. So that's a very intuitive way of explaining its intuition behind the internal covariance shift. I put also some link of the better explanation from NG Wu. Please have a look for that. So now we already talked about the idea of the internal covariance shift. How do we apply that is we try to make sure all the layers are doing the normalization as well. And that is part of the batch normalization techniques we're going to talk about now. So the first thing is we know there is already a techniques called whitening. So what whitening is doing is try to make sure that it's zero mean and unique covariance and also decorrelated between each features. So if we're gonna apply whitening to all the layers, that would be very computational expensive. Why? Because if you have a feature map really big, let's say you have 100 columns of different features and you have 10,000 samples, you want to calculate the zero means across them, then you need to first do a computation across this 100 times 1000 metrics to find out the means, and then you need to find out also the variance, and you need to make sure they are decorrelated, so you need to compute the covariant matrix, and that is very computational expensive, and we only talk about 100 times 1000. In reality, like image size, that could be 2 megapixel, 8 megapixel, things like that, and then it's very impractical to compute that all the time. So while training, that would take really slow. So we have whitening, but it's too computationally expensive. Then we want to do something simplified version from the whitening, and that is there's two assumptions for batch normalizations which learn from the whitening. The first one is we try to compute each feature independently. So instead of we just talk about if we have 100 features, and instead of compute all of them, we're gonna handle them one by one. So we only care about each feature independently. Okay, so the first thing is we try to normalize each feature independently. We don't care about the other feature. If you see the math here, the K means the features. So we don't care about the other covariance, metrics, those things. We assume they are independent. So we only compute each feature at a time. And once we have this formula, right? This formula is basically tell you, hey, I'm gonna do zero mean, and then I'm gonna make sure the standard deviations is we are focused on the our uh, it's divided by the variance, so we make sure that we are like a circle-like structures here. However, we need to remember one thing. Under so many layers of stacking the hidden layers, if you want to always force them, if you want to always force each layers to do zero means and standard deviations, that may be not the good idea because you want to provide certain degree of freedoms. I think this is kind of like similar idea of the ResNet we talked about in the previous videos. The ResNet has one very important idea is it allowed identity mapping once you go deeper and deeper because you don't know how complex things happen there. So you want to provide certain degree of freedoms. And inside the batch normalization, it's also do the same thing. It add two extra parameters during training to make sure that there is a degree of freedoms to allow identity mapping. So that is exactly these two parameters alpha, um, gamma and beta here. So if you do some math decomposition here, you can make sure that the y actually equal to um, um, without any without any normalization effect. So you allow the y equal to original x basically. If you can see here, if I use uh, gamma with these values and then beta with that values, and then if you plot into that formula, you can make sure that yk equal to xk. So there's nothing happen. And that is okay if the network in the end it learns, okay, I don't want to do normalization in this layer. Feel free to do that, right? So we provide a degree of freedoms of identity mapping. We don't force them to do the normalization all the time because you don't know inside the deep layers what would happen. And that's the idea here. And the second simplification is we talk about the whitening. You want the entire data sample to be calculated for the means and variance. But in the mini batch, in the reality, right, we don't have that much memory size during the training. So, and also in reality, we also using a SGD to do the training, right? So the mini batch is always be fit in to the while the training. So why don't we just calculate the means and variance across the mini batch, not across the entire data set? So we make sure we have enough memory. And second is we are aligned with SGD training process. So we only calculate the statistic inside the mini batch. Okay, so we bring up the intuitions. What is the idea of the batch normalizations? We have mini batch, we have some simplifications from the whitening. We only calculate the mini batch's mean and variance, and we allow these normalizations can do the identity mapping, and that is description inside this formula. So here we calculate the mean inside the mini batch. As you can see here, we have a different dimensions depending on what is your mini batch size. In this case, the mini batch size is m. So we calculate the features across those m's, and that is the mean. And we calculate the variance for that. We do the normalizations, and we allow the identity mapping here by imposing two extra parameters, which is gamma and beta. Okay, so by this formulas, what is doing the training doing, right? Training, we know that neural network training is the way that you draw out your computational graph exactly like this. And then based on your computational graph, you're gonna do a back propagation. And back propagation, what is back propagation is basically just a bunch of chain rules on a calculus, right? But first you need to understand what is the dependency between each computational node. Then you can calculate the chain rule for that. So the batch normalization, you need to understand that you basically are drawing, if this is a batch equal to 3 cases, and you have the weights are the same sharing across the different batches, and then you will calculate the result for that, and then you of course will calculate the mean and variance for that, and then after you impose the two parameters for allow identity mapping, and those things can be using the chain rule of the calculus to do the backpropagations. And something you just need to remember here, if you are talking about the means and variance, you see here it's always there. You are affected by the summations of those all batches. So it's not just z1 theta. It's not only affect the z1, because when you change the z1, right, you change the means and variance from across the batch. So if you change the z1, the whole mean and variance will change. So when you do the backprop, you always need to make sure that this update will impact all across the mini batch size, and that is the in sense for the batch normalizations, right? You're using a batch statistics to do the calculation here. But in reality, right, when you're doing the PyTorch and TensorFlow, you just call the API for they were doing that for you. I just want you to understand this is the math behind that. Okay, so when we talk about the training, right? We talk about the training before we say, hey, why don't we using the feature scaling to all the hidden layer, which is the batch normalization we're gonna apply. So the batch normalization will apply to all the layers before we are taking only X, and now we will apply batch normalization X for that. And now we talk about inferencing. So the inferencing, we are not using when we are not calculate the means and variance on the fly again, and because we will fix them and we will use the population means and variance while we do the inferencing. And then because during the training, we already trained the gamma and beta two variables, so we will directly apply for that. So that's why the training in the inference is so fast, because you are fix all the variables. It's basically normalization during the inference is, oh sorry, during inference is simply a linear transformations functions here. It's just a scale and shift here. So if we use the YOLO V4 terms, batch normalization is the bag of freebies. So batch normalization is only at cost during the training time because these two extra parameters, gamma and beta, and there's nothing more in the inference time. So batch normalization is a really benefit techniques because there's no extra cost for, or very minimum extra cost in the inference time. And that is what YOLO V4 call bag of freebies. If you are interested in what is that, what does that mean in details, you can check the YOLO V4 video. So now we talk about the inference here. Um, Basically, we talk about the training before. The training before is trying to collect in the statistics from the population mean and population inference variance, because you across each mini batch, right, you can update a global mean, and this global mean will what we call population. Population is statistics terms that across all the samples, right? Mini batch is just a, a batch of samples here. So we will collecting the statistics of the population means and variance. We will using that for the inference. So you can see here you have the mean and variance, and then you have a gamma and beta, which is learned during the training. So the whole inference is just a linear transformation here. And how do we apply the batch normalization on the CNN is there is some debate here. Basically, you can apply the batch normalizations before and after the nonlinear layers, which means the activation functions, something like ReLU, like sigmoid functions, those nonlinear functions. The reason behind that is because those nonlinear functions will let the distributions into not a Gaussian-like form. So you always want your normalization is apply something like Gaussian-like form, and that you make sure that after your normalization techniques, the Gaussian distribution is still Gaussian. So that's why in this paper, 2015, during that time, they apply batch normalization before the activation functions. So you can see here, this G is an activation function like ReLU, and then you have the weights times the input, and then you apply batch normalization before the activation functions. Okay, and for convolutional neural network, right? Convolutional neural network, we know that there is a spatial information across inside the image, in the same image, not across the batch. So you also need to take into account for the idea of the convolutional neural network is to collecting um, information from the same image because they have a special relationship there. So in the CNN case for the batch normalization, your we call effective batch size will be the batch normal mini batch size m as exactly as before previously times the feature map size q p times q. Usually they are square, so it's a p square here, but just generalize here. So the feature map size, why we do that is because the idea of CNN again, they want to collecting, they think in an image there is a special relationships within the certain window. So it's more likely you have a more correlated or more highly related features within your neighbors. So you need to make sure that this is also taken into account for the applying the batch normalization. Again, this is just math behind that. When you apply on the API, on PyTorch or TensorFlow, this is everything we'll handle for you. So we're going to talk about what is the benefits of batch normalization. First, it's allow a higher learning rate. Second is solve the gradient vanish point, vanish problem. And the third is you can care less during your weight initialization. And the fourth is it's a like a slight regularization for your training problem. And we're going to talk about the intuition or math behind that. So why it can allow higher learning rates and why it solve the problem of gradient vanish problem. That is because if you think about before, we talked about in the beginning the feature scaling is to make sure that the feature size is within a certain circle-like distribution. So when you have this circle-like distribution, you are you are okay. You have more freedom to do the weight initialization because you will be on each point of the circle, and you can apply a higher learning rates because you will towards the lower loss result when you go back to see that diagrams, right? So yeah, here is just some math intuition behind that. When you do some partial derivative, you have a less impact because of the Jacobian functions here. You can prove that, but from the intuition point, it's also back to this circle-like graph that because you will initialize on the circle place, so you are more resilient to the parameter scales and initializations. And the slight regularization effect is because mini batch is trying to collecting the noises or statistics across the different samples, and these different samples will bring some noises to the functions, and those noises might be very important for training because it's like a dropout. There is some noises during the training to make sure that the result of the training is more stable. So the experiments, we're gonna make it really fast here. The experiment's result is applying the batch normalizations, you have more freedoms we already talked about, to do the weight initialization, and you can apply the faster learning rate. So the result also is when you apply the batch normalizations, your training is much faster and the result is better. So when you see the inception model here and with the same baseline, the steps to achieve the same accuracy is like 3 times less here. So you can train the network much faster because this uh, normalization techniques you apply to each layers. Yeah, that's all for the presentation. So batch normalization is very important techniques that you apply normalization into different layers to make sure that your training is more stable and faster and better performance. Thank you.